So today we're going to be starting our first lab experiment of the semester. So this is buoyancy and Archimedes' principle. And so this video is going to be a description of what you're going to be doing. There'll also be a video of the procedure where you'll see me taking the data and you're going to record the data and you and your lab partner are going to analyze the data. And that lab report is going to be due on Monday. So with that, let's get to a description of this particular experiment. So the purpose of this experiment is to show that the buoyant force increases proportionally to the displaced volume of water or the submerged volume of the object, and then to use Archimedes' principle to measure the density of aluminum. So you're going to be working with an aluminum cylinder, and so it's got a hook, and so the hook is not really included in the measurements, so it's a possible source of error, so keep that in mind. Going back to what we discussed in lecture in chapter 13, if you have an object that's partially or entirely submerged in water, it experiences an upward force equal to the density of the water times the acceleration due to gravity times the volume of the object that's submerged. So we're going to consider an object of mass m and density rho, greater than that of water. It'll be held first in the air and then again while suspended in water. So what I do in the experiment, and you'll be able to take a look at the video, is I have what's called a force probe. And so the force probe, when you hold the object out of the water, it's measuring the object's weight. And then when you submerge the object in the water, it's measuring the net force, which is basically the weight minus the buoyant force. And so you'll get two measurements from that. And that's enough information for you to figure out the density of the object. So we're going to take the mass of this, and so I have a scale set up, so you'll see that reading, and you're going to want to record that reading, and the uncertainty in that reading. Measure the force on the probe when the cylinder is approximately a quarter, a half, 3/4, and fully submerged. So I had to cheat a little bit on this because I didn't have the graduated cylinder that we would use if we were in the lab itself in the basement of Smithtown Science. I had a cup. It measured, you could see the height of the displacement, and so you need to multiply the height of that displacement by the cross-sectional area. And so it's a circular cup with a radius of about 5.5 plus or minus 0.1 centimeters. So you're going to use that value when calculating the displaced volume. And so you're calculating the buoyant force. And again, that's just the difference between the weight measured in the air and the force measured when it's partially submerged. And measure the displaced volume for each case. And so there's a table in the write-up that you're going to use. Make sure you use the right units. Without units, a number is just a number. Doesn't mean anything. And so you're going to plot the buoyant force versus the submerged volume. You're actually only going to get 3 readings for 3 data points for this plot. But you should be able to see a linear relationship and get the slope. And so I'll put up an explanation for in Blackboard for how to plot a graph. I'll make sure that's up, and that if you look under content that you can see it. And so you should be able to do the plots on Excel or on the spreadsheet of your choice. Obtain the slope and the uncertainty in the slope, or the error in the slope. So what is the expected value? So remember, the buoyant force is equal to rho times g times v. So if you plot the buoyant force versus v, what do you expect the slope to be? And how close do you get to that value? So you're going to calculate the density of aluminum 3 different ways. The first is from Archimedes' principle. When the volume is completely submerged, and there'll be a second table for that, take the average value of the buoyant force that you get when it's completely submerged, and divided by the density of the water times G. And then the density is equal to the mass, which you measured on the scale, divided by V. For part 2, you're going to measure calculate the density by dividing the measured mass by the displaced volume. So how much water gets displaced. And there'll be a limit to the precision for that one. And then the final one is the density, so the measured mass divided by pi r squared times h. So I'm going to use a caliper. Some of you might not have seen this in Physics 1 experiments, but this is a more precise way of measuring lengths than a ruler. And so I measure the densities of the cylinder with the caliper, so the diameter of the cylinder and the height of the cylinder. And that enables you to get a value for the density. So you're going to calculate the density of aluminum 3 different ways. And if you try to do the error analysis with, as precisely as possible or as mathematically as possible, but if nothing else, at least be able to tell me which of these 3 ways of measuring it do you think is going to be the most accurate and why? And so that's what you're going to be doing for this report. Again, I have another video that's a companion to this that goes through the procedure. So you're going to take your data from that video, and then you're going to analyze the data. And if you have any questions, don't hesitate to ask me for help. Okay, so thank you. Like I said, if you have any questions, email me. Otherwise, have a good weekend, and we will get back to this next week.